This is an RNZ podcast.
Kia ora and welcome to Elemental from RNZ, in which we are exploring the extremes of the periodic table of elements and pondering existential chemical truths. I'm Alison Ballance.
And I'm Allan Blackman from the Auckland University of Technology. And as you might have guessed from my excitable co-host, this episode of Elemental, episode 92, is dedicated to Xenon and the letter X. Xenon. Right, where does it get its name from? It gets its name, obviously, from the Greek xenon.
Which means what?
Meaning stranger or foreigner. And this is because it was both rare and it has high density. And that's a feature that is uncharacteristic of the other noble gases.
Now, I'm dubbing this episode A Stranger in Search of Strange Particles. And we'll get to that later. But first, I'll take my usual, please.
The vital statistics.
Those are the ones.
Elemental symbol Xe for xenon and atomic number 54. And that puts it slap dab in the middle of Group 18. And being Group 18, that makes it a noble gas. And it was discovered, like nearly all of the others, by William Ramsay, who won the Nobel Prize in 1904 for chemistry, in association with Maurice Travers, and they discovered neon, argon and krypton as well, which makes you wonder why Travers didn't get a share of the Nobel Prize, but we won't go there. So it was discovered in 1898 by those two, and as per usual what they did was they extracted it from air. Now, given that xenon is present in air at a concentration of 0.0114%, this wasn't particularly straightforward, and in fact the discovery was almost an accident. Now, recall from our previous episodes that Mendeleev didn't include a space for the noble gases on his original periodic table because they weren't known at that time, and the reason that they weren't known at that time is because they don't react with anything. And when they were discovered, they were called noble precisely for that unreactivity.
But I feel a but coming on.
Yes, indeed, there is a but. And in fact, in the year 1962, an expat Brit in Canada showed that this wasn't the case, that in fact noble gases weren't quite so noble after all. So Neil Bartlett was his name, and he was the first person to make a noble gas compound. And he did this by reacting colourless xenon gas with red platinum hexafluoride gas, and this immediately gave a yellow solid when the gases mixed. And, in fact, the exact identity of this yellow solid is in doubt even today, quite remarkably. So this was the first of many xenon compounds, and it seems to be that most xenon compounds involve either fluorine or oxygen atoms bonded to the xenon. So Bartlett really started a whole new area of chemistry here, and shortly after his discovery of this yellow solid, one of Bartlett's new xenon compounds exploded, leaving him and his graduate student hospitalized with glass in their eyes. And this obviously was a lesson that noble gas compounds are often violently reactive. Now, Bartlett was nominated numerous times for the Nobel Prize, but unfortunately he never got it. And this is one of the great injustices of chemistry, in my humble opinion. Right, so noble gases, as we have talked about on Elemental, include helium, neon, argon, krypton, and then xenon in order of increasing density. So everybody knows that if you inhale helium, which is very light, you talk in a funny, high-pitched voice.
As you demonstrated in the helium episode of Elemental, episode 34, if you missed that one, folks.
However, the opposite happens with gases that are denser than air. So if you look on YouTube, you will find examples of folk inhaling xenon and then proceeding to talk in an extremely freaky, deep voice.
But you have no balloon of xenon to illustrate this in the Elemental podcast, Alan?
No, thanks. Anyway, I'd highly, in fact, recommend not trying this at home, as the very dense xenon can be rather difficult to expel from your lungs. Now, despite this, athletes apparently began inhaling xenon back in the early 2000s to promote the production of a hormone involved in red blood cell production. Suffice it to say, the World Anti-Doping Agency frowned on this, and in 2014 they added both argon and xenon to their list of banned substances.
Well, I think that's our chemical equivalent of a stranger danger warning, eh? Avoid breathing xenon. Now, apart from dubious YouTube videos of people talking in funny voices, what else do we use xenon for?
Well, pure xenon emits a blue glow in a gas discharge tube, and as a result of this, it is used in car headlights, flash bulbs and strobe lighting, as well as in ultraviolet lasers. Very energetic beasties, those. Now, xenon arc lamps have a colour temperature closely approximating noon sunlight, which is why they get used in things like movie projectors, especially IMAX projectors, and also in labs for testing things like new solar panels. And the most exciting application of xenon, I think anyway, is in xenon ion propulsion systems. And these are currently being used in spacecraft. Now, the way that these work, they involve positively charged xenon ions being accelerated towards a negatively charged grid at speeds of up to around about 140,000 kilometres per hour, which sounds like a lot. However, the actual thrust provided is relatively small, but you're in the vacuum of space, and this eventually results in speeds up to around about 10 times those that can be achieved by normal rockets. And more remarkably, the fuel use is absolutely minuscule. So the Dawn spacecraft that went to the asteroids Ceres and Vesta took only 425 kilograms of xenon for its mission, which started in 2007. And this kept the engines running for an astonishing 50,000 hours. Amazing.
That's very impressive.
I know.
Now, today's strange fact for our stranger chemical element, please.
Well, despite what we said before about not breathing xenon, it actually turns out that xenon can be used as a surgical anaesthetic, and indeed it's been described as an ideal anaesthetic. Those xenon atoms are just the perfect size to occupy particular protein cavities. And I've heard the xenon atom described as being like a smooth, round billiard ball with no sticky out bits. And so it literally just rolls into a protein. And this leads to the protein being shut down and subsequent unconsciousness. And now I should point out that as an anesthetic gas, xenon has to be used in conjunction with oxygen. So apparently there are very few side effects, and the patient can, this is a good thing, be quickly brought back to consciousness.
So why aren't we using this wonder anaesthetic all the time?
Well, simply because of its price. We talked about how rare it is in air, and that makes it very expensive.
Can I add my own strange and interesting fact about xenon?
Why, go ahead.
At the beginning of the podcast, I said that xenon was a stranger in search of a strange particle. And that's because, despite it being super expensive, xenon plays a key role in several dark matter detectors. So there's a project in Italy, it's even called Xenon in capital letters, and they are using increasingly large vats of liquid xenon, which they think will occasionally be able to trap WIMPs.
No, not WIMPs.
Yeah, weakly interacting massive particles as they pass through the Earth. So WIMPs, of course, are the particles that everyone thinks make up dark matter. And so in their last set of experiments, they used 3.5 metric tons of xenon in their WIMP trap. That's a very valuable vat of xenon. And at the moment they're scaling up, and their next vat's going to be 8 tons. That'll hurt the old bank account. But I really like this idea of using the chemical element that is called the stranger to try and trap these strange physical wimpy particles.
Very nice, that. And this strange episode of Elemental can be found again at rnz.co.nz/chemistry, or as a podcast wherever you like to listen.
We are rapidly nearing the end of our alphabetical chemical extravaganza, but we are not quite there yet. So stay tuned for the next episode, which is Ytterbium. I'm Alison Ballance.
And I'm Allan Blackman. Mā te wā.